All right, I think we are live. Okay, all right, so let me get started. My screen is still visible, correct?
Yes, sir.
All right, so the last time we had started to discuss about the transformation between the Earth-centered Earth fixed coordinate system and the northeast down NED frame. And we wanted to understand that this transformation really requires a transformation using what is called as the latitude and the longitude. And we were looking at how does this transformation occur. So we saw that primarily the first rotation is about the longitude, about the z-axis, followed by an angle which is given as minus mu minus pi by 2, where mu is the latitude. And the composite rotation matrix, which takes us from the NED frame to the Earth center Earth fixed frame, is given by the composite rotation of Z with respect to the angle L and the rotation about Y with respect to minus mu minus pi by 2. So that rotation matrix can be written out as this, and then we can kind of sum it up to put it out. What is the composite matrix looking like? Then we define that all of these coordinates or quantities which we are talking about, latitude, longitude, they are defined with respect to an ellipsoidal shape, because the Earth is not an exact sphere, it's an ellipsoid with the polar radius being slightly smaller than the radius in the equatorial region. And we looked at the difference was roughly about 27 kilometers or 22 kilometers. And then if we look at the idea that the latitude is called as the geodetic latitude and h is called the ellipsoidal height. So here, if we go back to this picture, the height h refers to the tangent plane drawn at the point of interest, which is perpendicular to the, from where we are drawing a perpendicular onto the ellipse. So the point of interest is here, and we are drawing a perpendicular to the ellipse, and then that angle that perpendicular makes with the equator is denoted as the latitude. So notice that the latitude is not the point, the angle of the line segment joining the center of the Earth to the point where we are connecting. That's not the latitude. Latitude is given by the normal. So we are looking at the perpendicular dropped from the point onto the tangent plane, and that angle is mu. All right. Okay. Then we discussed about what is the value of this radius of curvature and how do we estimate it with respect to the latitude and the longitude and the quantities related to the Earth. And then we figured out what is the longitude, and we figured out the idea that the latitude and the height are implicitly correlated, which means that the latitude actually depends on the height, and similarly the height depends again on the latitude. So there is a need to solve this system of equations iteratively until the convergence occurs. So then we discussed about the idea that what is that algorithm? So we've given a points xe, ye and ze. We start off with that and compute what is called as p, which is square root of xe square plus ye square. And from that we get the initial approximation of the latitude, which we call as mu 0. And there we are taking as tan of mu 0 is equal to ze by p times 1 minus e square inverse of that. We compute the value of n, which is the radius of curvature, using this initial approximation of mu 0. And then based on the computation of h, we plug these things into the formula for h, the value of mu 0 and the calculated value of n, in order to get the ellipsoidal height. Notice that this is the height of the object from the tangent plane, where the we are looking at the ellipsoidal tangent plane. That is what we are really looking at when we say H here. Now, we compute the improved estimate of the latitude by actually taking into account that H is not 0. So we plug the value of N and H into here to get the new value of the improved estimate of the latitude. And then we check whether the latitude changed by a significant amount or not. If the change is not much significant, is less than the tolerance value, we assume that we have found the right latitude and we keep it. If not, if this value is greater than epsilon, and epsilon is some tolerance value that we choose, then we have to iterate. And what do? We take mu and store it in mu0, and then start back at steps 3 to 6. So we again compute the value of n with the new mu0, and then compute the value of h with the new mu0, and then compute the improved latitude mu, and again check for this condition. So we keep on doing this until a convergence is achieved. This algorithm which we have seen right here is just one of the many algorithms which are available to compute the latitude and longitude. This particular one was taken from Hoffman and Wellenhoff et al. 1994. This actually is a book, we think, which is called Global Positioning Systems, and it's a pretty detailed book and talks a lot about how do you understand what is the how do you estimate these quantities from how do you shift from one frame to the other frame. So how do you take latitude, longitude, and height and compute the coordinates of the point in the Earth-centered, Earth-fixed frame, or vice versa. Okay, the height which we do get, I do want to talk about that today. So this height we are computing with respect to the ellipsoid or the global ellipsoid of the Earth, which we are terming as WGS 84. Notice that it's only an approximation of the mean sea level, but in reality the mean sea level may deviate up to more than 100 meters than what is computed using the reference ellipsoid. So therefore, since when we are talking about local navigation, we are mostly interested in the height from the sea surface, right? So it makes sense to actually find out where the correct sea surface is rather than estimating it from an approximate sea surface, which may be having considerable difference from what we saw here. So for example, if we look at some of the tests which our research group had recently performed over the weekend, you will see that these values for H came out to be negative, which means that the reference ellipsoid was higher up, whereas our actual lobe surface was much lower. So these sort of things need to be corrected for in order to get the correct value of the mean sea surface level, and that we do by considering the Earth's geoid instead of the ellipsoid WGS 84. So the initial computation is computed using the WGS 84 ellipsoid, but we have to correct it using the Earth's geoid. Now, what is a geoid and how is it different from the ellipsoid? Now, ellipsoid was simply an ellipse which we were rotating about an axis of symmetry to get the ellipsoidal shape, whereas the Earth's geoid is the shape the ocean surface would take under the influence of Earth's gravity. Okay, so it's slightly more abstract concept. So it is the surface that we typically choose in surveys as the zero reference level. So most surveys choose this value, the geoid surface, as the reference zero level. Okay, now the question of how to compute the geoid and how do we actually get the geoid surface is quite a complex procedure, in the sense that the geoid basically tries to see that we have the same gravitational magnitude all over the surface, and the gravity vector is always perpendicular to the geoid. So you have to really do some calculations, surveying, in order to find out where the shape of this Earth's geoid is locally. So this cannot be computed mathematically. It requires measurements and then followed by calculations. But in several cases, you will have nowadays a well-documented geoid is available for different parts of the geographical regions. So that could be obtained, and then you can use that to look at what the actual geoid surface looks like. So if I come back and do a pictorial representation, so let's say this is my ellipsoid surface, then the geoid might actually look like something like this. Notice that the geoid actually does depend on the hills, valleys, and other things. So suppose I had the Mount Everest, and then I have the Marina Trench, then the geoid would kind of somewhat follow these architectures in order to make sure that the gravitational vector is pointing straight down. Whereas all those fluctuations or undulations, these undulations will not be there on the geoid. So on the ellipsoid. So no undulations. On the ellipsoid. This is a smooth surface, okay? Whereas the geoid is not as smooth, it does actually take into account how the continents are structured and how the actual Earth looks like. And then based on that, we are kind of figuring out where the geoid's reference location is located. So in general surveying, so suppose I'm doing a building or I want to find out where the drone is located over a certain height, I'm interested really in the height from the mean sea level. Mean sea level, right? So that mean sea level datum is defined with respect to the geoid. So in order to get that value, I have to make some measurements and calculations. Gravitational measurements and calculations are required. And through that surveying process, you find where the geoid is at a particular location. Now you have to transform the height that you got previously, the ellipsoidal height, that has to be transformed into what is called as the orthometric height. Or this is the height with reference to the geoid or with reference to the mean sea level. This is the height which we are interested in many applications. And that height will be different from the ellipsoidal height we found. And that will be different by a value usually called as the geoidal height, where we are basically saying how much is the geoid away from the ellipsoidal surface. And this quantity may be positive or it may also be negative at certain locations. Okay, and there is a small angle between these two, depending on where the normal vector is pointed, and that is usually taken as the deflection of the vertical. But usually these can be assumed to be approximately zero for most of the things which are happening on the Earth's surface. Because if you actually look at what is that angle change in normal between the geoid and the actual surface, it's less than 30 arc seconds across most of the Earth, so it can be neglected. Okay, is this making sense? Yes, no?
So like this geoidal, like the surface kind of thing, like if we are doing it by measurement, so like we must have taken, like they must have been taking measurements at certain points, right? So it will not be like is it some kind of fitting like in the parts in between?
So have you ever seen before a building is constructed or some construction activity takes place, they'll come with a pole and they'll set up a tripod and they'll stand far away from the pole and make some measurements? Yes? That measurement is nothing but these surveying applications. So what they are doing there is they are looking at a reference height, which the pin location where they are holding it, they are looking at what is the GPS coordinates there. In addition, they are measuring what is the accelerations from the gravity, and then they are making the corrections inbound to look at what is the actual height of that point from the geoid surface.
Oh.
Okay, so most surveying applications, when you are using that, you have to have this correction factor which is required. Okay, for our purposes, this will not be too useful because we are mostly interested in the latitude and the longitude and quite less in the height, because unless and until we are going deep into the ocean. So unless until we are looking at underwater vehicles which are going deep into the ocean, we are not really concerned with the height, and also underwater you don't get GPS. So you really can't triangulate using the GPS. Right? So this is something of an extra information we are just adding here to understand that such a concept exists. Like an orthometric height exists, and that is usually taken from the mean sea level, and that mean sea level doesn't actually coincide with our ellipsoid. Our ellipsoid is a smooth approximation of the Earth, but that necessarily does not mean that that's where the Earth's surface is. Right? And that difference in the Earth's surface, or that difference in the zero value of the mean sea level, is given by the geoid surface. So I'm only introducing this as an abstract concept. Okay? And then based off of that, we measure base our height measurements whenever we are interested in the surveying applications. For most of our studies, when we are looking at the marine crafts or when we are looking at in the deep oceans, this really will not be much relevant because height is not the biggest concern for us, especially if we are on the surface. Right? And besides, if we are on the surface, we exactly know where the mean sea level is, so we need not bother ourselves with too much. So in that sense, it's good to have an understanding of this, that there is something called a geoid based off of which we mark off the mean sea level, but that's not really much required for most marine applications. We are mostly interested in the X and Y location of the craft using the GPS. Did that answer your question somewhat?
Yes, sir.
All right. Any other queries? Now's the time to ask. All right. So this geoidal height is formed through what is known as a datum transformation, which is usually seen in the surveying applications. We'll not be spending much time to discuss what this process is and how that happens, because it's not much relevant for us. It's just for the sake of information completeness that we have covered this height transformation. So just keep in mind that whenever we are looking at a height value from the GPS, for most surveying applications, they are referring to what is called as the orthometric height. This orthometric height is what they want to measure, which requires them to have a consideration as to where the gravity vector is pointing, and accordingly have a correction of this ellipsoidal height in order to get the orthometric height. Okay, all right. Now let's come back to our point that suppose we know the latitude, longitude and the height. How do I compute the coordinates of the point in the Earth-centered, Earth-fixed frame? And there you can see that this is nothing but n plus h, where n is that radius of curvature, plus the height above the tangent plane, times cosine of mu times cosine of L will be the x coordinate. Same thing, but sine of L will be the y coordinate. The z is a little tricky because it is an ellipse, so you have to make sure that the geometry of the ellipse is taken into account properly. So r e square by r e square times n plus h times sine of mu will give you the z location. So if I know the latitude, longitude and the height, I can compute what are the coordinates of the point in the Earth-centered, Earth-fixed frame. Previously, when we had looked at that algorithm, we were looking at the other way around, where we know xe, ye, and ze, and we wanted to compute the latitude, longitude, and height. right? So here in this case, we are looking at the opposite. If I know these three, how do I compute x, e, y, e, and z? For a ship which is floating on the surface, this h is nothing but the vertical distance from the center of, from the sea level to the origin of the body coordinate system. So what is the height between the sea level to the body coordinate system origin? That is what we are looking as the height. Okay, is that clear up till here? Yes, no? Something is unclear, just tell me now. Is this part clear how these formulas have come in? Is it clear? Yes, no? I guess not much. Would you like to see that again? How these have come through?
Yes, sir.
Alright, it's nothing but our ellipsoid picture. We go back to our ellipsoid. Correct. So if you look at it, I want to look at a point x, e, y, e, and z, e, and I want to find, so that if I take the point from here and I construct a triangle, okay, the hypotenuse length is n plus h, correct? Yes.
Yes, sir.
So what is the vertical extent and what is the horizontal extent is what I want, right? Especially from this point is what I want. So let us say that my horizontal extent, let us say for example, let's say YE was 0, okay? Which means that it was actually pointing towards the uh, Greenwich meridian. So my point was actually along the Greenwich meridian. Is that making sense?
Yes, sir.
Okay. So if it is along the Greenwich meridian, then what will be my XE? XE is the distance from the center of the earth to this line, correct? Because I have to measure with respect to the center of the earth, right?
Yes, sir.
Okay. So based on that, can we tell what is XE in this picture?
Is n plus h cos nu.
N plus h times cosine of mu, right?
Yes.
Right. Now suppose that y was not 0 and there was actually a longitude. What will happen? I have to take a component of this along the by the angle L to get xe, and along y I would have had to take the sine component, isn't it? So which means that suppose the vector didn't lie in this lane, but it actually lies somewhere here. So I would have to take components in these two directions, right? Assuming this is my y-axis. Does that make sense? This and this?
Yes, sir.
For everybody.
Sir, I am confused. Like that, for y is equal to 0, where will that point lie? This xe 0 and ze.
Okay. All right. Let's do one thing. My picture doesn't seem to do it justice. Let's go back to the Fawson's picture. That will make it a little bit better. Okay. Give me a second, guys. Let me pull up the picture properly.
So this L is the azimuth angle, right?
L is the longitude.
Will they do they refer it to as azimuth also?
No, L is simply the longitude. That's all it is.
Like during that coding for the station keeping, I reference like online code for it. So in that, this cos and sine, these were uh, like referenced as azimuth. So
Okay, you can just see it here. Okay. What my point is that L is the longitude. So for example, let's say I'm looking at a point further along this line. Okay. So let me try to draw it. Okay, so that is my point, XE, YE, ZE. Okay. Yes.
Yes.
Okay. Now, what I'm saying is this distance from this point to this point, that is N. And from this point to the actual point, that is H. Correct?
Yes.
So I have N plus H into cosine of mu by this angle. I am actually making a projection along this line, isn't it?
Yeah. Yes, sir. Yeah. Okay.
Right? Now that projection along this line will have two components. One along, so let's say that if I made the projection, my point comes out to be somewhere here. Okay. So when I project that into the y-axis and that into the x-axis,
Yeah. Yes, sir. Yes. Understood.
that will be my ye and that will be my xe.
Yeah, that will be sine and cosine of L. That.
Correct. So that is all I am saying. So cos of mu times cosine of L would be xe and ye would be the same thing, n plus h cosine of mu times sine of L. Okay.
Yes, sir.
Now the next thing is that I take this fellow and I take a projection about the z-axis. Correct? That will give me ZE, right?
Yes, sir.
So that
Yes, sir.
will be nothing but, in ideal conditions, it will be n plus h times sine of mu. Correct? So I'm simply taking this vector and projecting it onto here, no?
Yes, sir.
But here the problem is that the ellipse is not flat, or at least our Earth's ellipse is not flat. So when I'm taking the projections, I need to make sure that this thing comes out to be rp square by re square in order to account for the difference in the two radii when I computed the local radius of curvature. So that plus h times sine of mu is what it is becoming. Just by the geometry of the ellipse, that's all.
Sir, I don't understand this part.
See, originally when we were trying to look at the radius of curvature, this is taking a plane which is tangent to the ellipse, isn't it? Correct? This plane here is the tangent plane. Correct?
Yes, sir.
That tangent plane, when I draw the normal, it will not intersect here. Why? Why it will not intersect there?
It is not exact sphere.
Because the
Ellipsoid.
Earth is not an exact sphere.
Exact
Right?
ellipsoid.
Correct. The Earth is not an exact sphere, so that is why it will not intersect there.
Oh, yes.
Right? So therefore, when I want to compute the orientation in the z direction, I want to look at, so what it is essentially saying is that when I'm trying to look at this, where did this go? 1 second. Okay, n was given by re square by re square cos square L, right? I'm not wrong. See it once. Cos square mu. Cos square mu plus re square sin square mu. Square root of that. Okay? Yes. Yes, no. Okay, now this point, since it does not coincide with my center, it is off by some distance, isn't it? When I take the projection about the z-axis.
Yes.
Correct? And that difference is coming primarily because the Earth is not an ellipse, is not a sphere. It is an ellipse because this side the radius is RP, the other side the radius is RE, which are not equal. That is why this gap is coming. If Earth was a perfect sphere, this point would lie exactly here, isn't it?
Yes, sir.
So that is the difference. That height has to be accounted for when I take the projection on the z-axis. Because I don't want to be computing the z point from here. I want it to be computed from the center of the Earth. Yes?
Yes, sir.
So that is the part which we are subtracting. That is why this ratio will be less than 1. This distance will be less than n. Whatever is that distance less is that value. So what is that distance between here to here? Actually, if I wanted to compute, it will be 1 minus rp square by re square times n. Is that making? That distance is coming primarily because it's not an ellipse. It is an exaggerated picture that this distance is looking much larger. But that is, distance will be very small. Anand, making sense?
Yes, sir.
So when I take a projection, I have to subtract the distance out before I can compute the z coordinate. Because the projection will include the z coordinate plus this value.
Got it, sir.
Okay, so that is why you get this rp square by re square times n plus h times sine of mu 0. That is the value of z. Okay, I hope that's now clear for everyone.
Yes, sir.
Okay, all right. So let me come back here. Okay, so that is how we are getting these three equations to transform the latitude, longitude, and the height to xe, ye, ze. And we also saw how to transform the xe, ye, ze into the latitude, longitude, and height. Okay, now that is well and good, but really when we are doing the navigation, I don't want to be looking at a latitude, longitude, and a height and be trying to figure out how my distances are changing. So for example, let's say my craft moves from here to here to here. I want to find out what is the distance between these 2 points in the n frame rather than a difference in longitude. I don't want to calculate the longitude. Here is L1 mu1, let's say L2 mu2. I'm really not interested in calculating L1 minus L2 and mu1 minus mu2. These values don't make much sense to me unless I actually convert them into a distance, isn't it? Is everybody with me so far?
Yes, sir.
Okay, so in some sense, I really need to convert this xe, y, z points into the n frame. So I really need the x coordinate in the n frame, y coordinate in the n frame, and z coordinate in the n frame. That's what I want to find out. And how do I do it? And how do these latitude, longitude, and height play a role when I'm doing the conversion to here? That is what we'll talk about now. Okay, and here there are two ways to do it. One is that suppose I'm looking at very large distances over which I'm going, let's say. Okay, so let's say this is my sphere. Obviously, a drawing could be better. And let's say I'm going over very large distances, all the way from, let's say, North America, Canada to Australia, things like that. So then what happens, the curvature of the earth really does play a difference. I can't convert the entire path onto a flat region and assume that I can do local navigation, right? Because these distances are really large and the earth's curvature is important. So this is when I will need to have a transforming frame. I have to locally look at certain time, construct an NED plane at that location, find out what is the value of latitude, longitude at that point, and then do local navigation around it. And again, as the distance changes, I have to shift my reference point to the new point, formulate the plane there, and then start doing the local navigation about that plane. Is that making sense? Yes.
Yes, sir.
But suppose, let's say that I'm starting here and I'm still staying very close to it. I'm only doing a local navigation in this region. So for example, let's say that we took our vehicle ASV, the autonomous surface vehicle that our research group is building, and we take it to the lake. We know that the lake is no more than 300 meters across 100 meters, let's say, right? In this case, we know that over this small a distance, the curvature of Earth is not very significant. And I can assume that I'm more or less taking a point about which I construct an NED plane, and I just transform all the GPS measurements which I get into that NED frame, which is fixed at some L0, mu 0. As long as my vehicle doesn't wander off too much from these two coordinate systems, from this latitude and longitude, I should be fairly straightforward to put everything into this plane. Yes?
Yes, sir.
Yes.
Right? So there are two ways to really look at it. And so therefore, we can assume that the NED tangent plane is fixed on the surface of the Earth at some point L0, mu 0. And then we can do the transformation of the positions and velocities into that NED frame when we get measurements from the GPS sensors. And if we wanted to do that, we have to be only careful that our vehicle doesn't wander too much from L0 and mu 0. In this case, our rotation matrix from the N frame to the E frame is a constant, in the sense that given a particular L0 and mu 0, the rotation matrix doesn't keep changing with time. Is this making sense? No? So an example would be, suppose I wanted to look at ASV navigation for my craft in the lake on the campus. I may put my base location L0 mu 0 as the department. I may choose that let the department be the point where I fix my base value, and from there what is the change in longitude and change in latitude that I am measuring, and I want to convert that into a distance in the NED frame. Not clear?
So this L naught mu naught will be the 0, 0 of this tangent plane.
Correct. It will be the 0, 0. So that is where we'll construct the tangent plane. So we'll construct our tangent plane at this location with L naught mu naught being the center at which the tangent is occurring. And then whatever little navigation that we are doing, we are mapping it into that plane. So even though the actual L0 and mu0 will be slightly off, but as long as these distances are not too large, the radius of curvature of the Earth will not start affecting. So you can think of it like this. So let's say the Earth's curvature looks like this, and I have a tangent plane here. Okay, if I am within this region, let's say, then I can assume that whether the point is here or here is very close by. Correct?
Yes, sir.
But
Yes,
if
sir.
I start wandering more away, then these distances will start making a difference. Okay, a typical order is this is about 10 kilometers if I am with respect to my L0 and mu0. I may be able to get away by just looking at the latitude and the longitude difference and mapping them into the NED frame, which is defined with respect to this base point. But however, if my craft starts to wander more than 10 kilometers away, so let us say it is going from one continent to another continent, then I can't take every point and map it into the flat earth plane. Then the distance will be wrong. The distance from here to here will not be the same as the distance from here to here. Are you following me?
Yes, sir.
So so whenever we are doing local navigation, where the distances are not too large, so within a 10-kilometer radius, then we can get away with the fact that I can map all the latitudes, longitudes to one NED frame. So instead of, as my vehicle traverses, it will have its own latitude and longitude value, right? I will not be looking at what is the new rotation matrix with that latitude and longitude, but rather I'll be fixing the rotation matrix at the value L0 mu0 and use the same for all the latitudes and longitude values which I get within the 10-kilometer radius. So that helps me map my latitude longitude pair into a xn, yn and zn value. Does that make sense? Okay. All right. For everybody, nobody is lost, is it?
No, sir.
I've not heard back from Joel.
Yeah, it is clear, sir.
Okay. All right. Okay, so in this case, the kinematics for the translational velocity, if I want to express them, I know that the position vector from origin E to origin of B, expressed in the E frame, the derivative of that position vector will be given by the rotation matrix from N to E times the rotation matrix from B to N times the velocity of the body fixed origin with respect to the Earth center expressed in the B frame. Okay, I'm just taking two transformations. I'm going from the B to the N frame and from the N to the E frame to get my final quantity in the E frame. By now, this should be more or less clear. There should be no questions on this, correct?
Yes, sir.
All right. And this sort of a kinematics which we are looking at is fairly good enough for dynamic positioning applications, which is what our course is all about, right? We are looking at dynamic positioning applications where we have maybe an offshore structure or a what you call a moored system, an FPSO system, and we want to kind of make sure that we have the vessel is moving in a certain region, but it is not really drifting away by large areas. So we are still well within this 10-kilometer radius for us to make the approximation that we can keep these rotation matrices as constants. They don't change with time. Okay, this will not be constant, but this one will be constant. So from the E frame to the NED frame, when I make the transformation, it is simply based on a fixed chosen set of latitude and longitude. So which is chosen as the reference value. All right. And when we have that sort of a situation, we can, given a latitude, longitude, and a height, we should be able to compute what is the value of the xn, yn, and zn. That is what we are interested in. So here you can see that when I know what the delta L is, I can define L as L naught, which was the reference longitude, plus the change in longitude. And similarly, mu is defined as mu0, which is the referent latitude, plus the change in latitude. And I take what is called as the smallest sine angle, which means that if that value is going beyond pi, or if it is going beyond minus pi, I try to convert them so that they are in this range from minus pi to pi. Is that making sense? Is this small sine angle thing making sense? I just want to be inside minus pi to pi. So if I have something as 2 pi, I convert that value into 0 or pi plus x. Then I simply convert that value into the range minus pi to pi and see where it falls. Okay. And the height is taken as the h reference minus the z value. So here what we are doing, given a value of xn, yn, and zn, how do I calculate the latitude, longitude, and height? And then we will discuss the other way around as well. Okay. So given that I know these, okay, how to compute the latitude, longitude, and height? So if I know the reference location L0 and mu0, I can calculate delta L and delta mu as shown here. So delta L is the y coordinate times a tan 2 1 minus rm times cosine of mu0, and delta mu is xn times a tan 2 1 comma rn, where rm and rn are the radii of curvature in the meridian and the prime vertical plane. Which means that if I were to look at a sphere corresponding to the radius as the equatorial radius, then that radius would be given by Rn. So the radius of curvature in this case will be given by Rn. Similarly, if I have the radius of curvature of the Earth defined as with respect to the polar coordinates or the polars where the pole is located, then the radius of curvature with respect to that plane would be called the Rn. Okay, and then those two are related basically by the eccentricity of the ellipse. There is specific equations which tell you how they are coming. And what this is doing here, the transformation into latitude and longitude, what it is doing is it is taking into account how much of that curvature is coming into the picture. So if I take a surface of the earth and I move a unit distance away, okay, versus I move unit distance away along the earth's surface, what is that difference? That is what it is trying to ascertain. When this difference is small, I can get away with the fact that I am simply taking a tan 2 of 1 minus this. Okay. Yes, no.
Yes, sir.
Okay. In essence, just think of it in this manner, that this is accounting for the curvature of the earth. These two terms which you are seeing, they are accounting for the curvature of the earth. Okay. So given a set of NED values, if I know where the location of the craft has traced, and if I wanted to convert that into latitude and longitude, this is how I would do the conversion. Now, this is not a class in geodesics, so I'm really not going to be going into the derivations of all these. You'll have to trust me. Otherwise, you can look at that GPS book which I was suggesting by Wellenhoff. That has the information as to why these relationships are coming in and how do you prove them. But for our purposes, we really need an application of it. We are not really interested in deriving these equations. For our purposes, if I am given coordinates in the NED frame, how to compute the latitude, longitude, and height is simply given by these three equations. Okay, and similarly, if we want to convert the other way around, if I know the latitude and longitude, I can calculate delta L and delta mu, and from there I can find out what is my xn, yn, and zn. You will just see that these are inverse relations of the previous ones. So xn will be delta mu by this, yn will be delta L by this, and so on and so forth. Okay, it's basically a conversion factor, how to convert a latitude, longitude, and a height value which you read from your GPS sensor into the NED frame would be done by this. So these would be the most important equations which we will require in our applications. Okay, so given a latitude and a longitude which is read from our GPS sensor or let's say on board the craft, how do I convert that into how much my craft has actually moved across and where is it located in the NED plane? That I can compute using these values. Notice here that this Rn and Rn basically depend on the radius of the earth and the eccentricity of the ellipse and where the latitude value is currently. Okay. Now, I know that I'm not really going into the derivations of these equations, how they have come about. They're not relevant for our course. If we are talking about a geodesics course, then it makes sense to talk about them. Otherwise, I think they're not too important for us. So let's keep in mind and let's try to restrict our exposure into these things. We are trying to take a exposure into how to do these conversions, but we're not in a geodesics class that we want to really understand them completely. If anybody is interested, feel free to look at the book that I have just suggested or the reference that I've provided. They'll have more information on how this thing has come. Is that making sense? Is that fair enough?
Yes, sir.
Yes, sir.
Yes, sir.
All right. So then in that case, we will try to stop here. Any questions before I stop?
Sir?
Yes.
Sir, in the Moodle website, the only 15 pages of that notes is available.
Only?
The first 15 pages of your notes is available.
All right. I will update that today. Yes. Anything else?
Also, sir, can you upload the class video of last Friday's class?
Yes, I'll upload that as well. All right. Anything else on the class today? Nothing? Okay, let me stop recording in that case.